Hello friend, welcome back to Algorithm Visualize. This is the golden sound. Let's continue with another recursion example. So let's try to calculate n to the power of, or 2 to the power of n, okay, recursively. So a function power of 2, okay. So yeah, that's n int, and we return an int. So for example, 2 to the power of 3 is 8, right? Yeah. Base case, when n is 0, it should be 1, right? 2 to the power of 0 is 1. Any number to the power of 0 is 1, okay? So now it should be easy, right, to write the recursive case, okay? And 2 times power of n minus 1, right? N minus 1. It should work. It cannot be wrong. Test power of 2. So xct assert equal 8. Power of 2, n is 3. Yeah, let's run it. Command S to save and test. Yes, it passed. Okay, but wait a minute. What is 2 to the power of like 50? I don't know the answer. Let's run it to fail it and copy the answer. This one. That's a huge number. Okay. Yeah, it passed. And if we print out n here, like that, and we can see, right, every time the recursive function call is made, we can see an output here. There should be, yeah, 50 of them, kind of 50. There are 51 lines of output here. Can we do better? This is like a linear. The number of recursive call is same as this number, almost. In computer science, there's a huge, super good strategy called divide and conquer. So what if we want to calculate like 2 to the power of 16 or 8? So this one is 2 times 2 times 2 times 2, right? And copy and yeah, just save some typing. It's that. So to get that, we use 2 times the result of the rest provided, right? The rest provided by the recursive calls. And to calculate that, we just need the result of this part, the sub problem, and then multiply 2. And we can make a closer observation. What if we know this part? Do we need to recalculate that recursively? No, right? If we know that, we can just do. We get the result of that one, right? And say this is A. We only need to do A times A to get the whole result. Okay, let's give it a try. So put 8 here and see 2 to the power of A. It should be 256. Okay, let's make sure I am correct. Yes. So that many of recursive calls. Yeah. Now how do we use the divide and conquer strategy here? So we can do something like that, right? Let product equals or result result equals power of 2 and half of it, right? So each time we cut half of that. So that with that result, we only need to do a simple multiplication like that. It should work. Oh, this might be caused by the base case. Yeah. The result is 1. So this can be fixed by simply change our easier base case 1, right? When n is 1, we return 2. Yeah. Try it again. So yeah, now it passed. So yeah, this is not a big deal, right? So when n is 1, we can stop. We don't need any help to return the answer, right? 2 to the power of 1 is 2. But now what if this one is not 8, right? 2 to the power like 13, an odd number, or even like 10. The next time after we cut half, 2 and 2, so we have 10 of them. If we cut this one to half, the first time is even number, the second time is 5. We have 5 2's. How can we handle that? Okay, so don't forget that one or 10. So for example, it's 11, right? We can do 2 times that, right? So this part is an even number, 10 of them. So by pulling out 1 2, the rest is an even number for any odd number here. So we can use this observation to handle that. So result is that, okay. So if n is an even number, if n is an even number, we can just do that and that. Otherwise, we can do we can get the result like that, right? N minus 1. N minus 1 is an even number. Yeah, it can be divided by 2 evenly. So now we just return 2 times result. Okay, now check here. Run it. It works. What about a big number, 50? Yeah, 1125. That thing, we met this guy before, yeah. So run again. Now check here. The steps of that is like a logarithm. So we changed, right, the time complexity from linear to logarithm. So we cut half and half. Yeah. So the number of steps decreases so fast. We improve the performance here. And this is a better implementation of 2 to the power of n recursively. Thank you for watching. See you next time.